Welcome to my mini lecture Tomography 206. Here I continue the story that started with Tomography 202 video, where we saw that ghosts and ill-posedness can cause trouble even with a 2x2 tomographic grid. In this video we will see how to use total variation regularization to solve the inverse problem.
Recall our square-shaped patient. Our imaging geometry has 4 X-rays. In the video Tomography 202, we built a matrix model for this measurement. Also, we found out that the matrix A is not invertible. There is a non-trivial kernel. That's why we had ghosts, leading to non-uniqueness of the inverse problem. Non-uniqueness presents us with a tough question. How can a reconstruction method pick out the correct image among all that match the data? Note that the left half of our original target has small numbers, so it's like soft tissue such as muscle. Bigger numbers in the right half indicate hard tissue like bone. We will reconstruct with total variation regularization, or TV regularization for short. It promotes a small number of constant areas separated by sharp interfaces. To illustrate the workings of TV regularization, we cook up 2 examples on the side of the original patient. The flat candidate is good for total variation since it has just one large domain of all same numbers. The spooky candidate comes from adding a ghost to the original. TV regularization is based on minimizing a sum of data penalty and prior penalty. Let's see what we get for our 3 examples. Let's compute the data penalty for the true target. Calculate the first X-ray measurement. The result is 8, shown in blue. Subtract the original measurement and square the result. We get 0. Calculate the second row sum. Subtract and square. In this case there are no differences, so we get 0 data penalty. Total variation prior penalty is the sum of jumps between neighboring pixels. Here we get 4. The second one adds 5. Here we get 0 and then 1. TV prior penalty adds up to 10. So the combined penalty for the true target is 10 euros. For the flat candidate, this X-ray measures 6. We subtract the actual measurement, that was 8, minus 2 squared gives 4. The second ray gives minus 3 squared, so add 9. Then we get another 4, and the fourth ray gives again 6 as the measurement, but the originally measured data was 13. Squaring minus 7 gives 49. Total data penalty is then 66. There are no jumps between pixel values, so the prior penalty is 0. Combined penalty for the flat candidate adds up to 66 euros. The spooky candidate produces the same measurements as the original patient, so the data penalty is 0. The spooky candidate has 3 separate areas of constant attenuation. Therefore, there are pixel differences adding up to 18. We get a combined penalty of 18 euros for the spooky candidate. So we see that the original target has the smallest penalty out of these 3, which is a good sign. The flat candidate looks like tissue, but fails the data penalty. And the spooky candidate cannot fool TV regularization. It has bigger penalty than the original. But in practice, we don't have 3 candidates. We need to calculate the reconstruction from data, whatever it is. We formulate TV regularization as a minimization problem. The unknown pixel values are called x1 to x4, and formulas are written for the two penalties. We must find such values for x1 to x4 that the combined penalty is as small as ever possible. Here you see the minimizer. These pixel values give the smallest combined penalty you can ever find, whatever you try. Note that there are two internal organs, left one soft and right one hard, as in the original.
We will see in a later video how to actually solve this minimization problem of total variation regularization. Let me add a historical note. Total variation regularization was first introduced by Rudin, Osher and Fatemi in 1992 in the context of image noise removal. A bit later, in 1998, Delony and Bresler used total variation in X-ray tomography. The next ones were Persson, Boone and Almqvist in 2001. And actually the first time when TV was used for real measured X-ray data was done by my team in 2003. Since then, total variation regularization has become a basic method in iterative reconstruction in tomography.